last panel of the day, also probably one of the best, and I'm so honored to be with all of you today. It is absolutely incredible what I got to witness on stage a few hours ago with the signing of the MOU. I'd love to just take it down the path here and for each one of you to introduce yourselves, and then we can kind of get into the incredible work that you guys have all been doing. And I will underscore, for years, the people on the stage have been doing this work in quantum advancement. And this is not something new. This is not just a, hey, we heard about quantum, and so we're going to quickly shift our institutions into talking about quantum and getting buzz and students interactive. But it is something that they have all been doing for many years. So my hope and dream is for the next couple of years to seeing their output, doubling or tripling, no pressure. But I would love for you to start first and go ahead and introduce yourselves and the universities that you're with.
Sure. My name is Hebin. I'm a professor of physics at the University of Miami, and my research group works on experimental quantum research.
So I'm Kathleen Am. Oh, sorry. What happened there? Okay, can you still hear me? Okay, great, with no echo. So I'm Kathleen Am. I'm the director of the National High Magnetic Field Laboratory that's headquartered at Florida State University, and we also have our partner institutions at the University of Florida and Los Alamos National Laboratory. I'm very proud that I actually was a PhD graduate from FSU over 30 years ago working on superconductivity and actually making conductors for superconducting magnets. So I've been in condensed matter physics and all of this right from the beginning. I then went and was at GE for almost 20 years with leading the whole MRI team there at the GE Research Center. Then went to do particle physics for a while at Brookhaven National Labs, and now when this job became available a little bit over 2 years ago, I said I got to go for it because this is the lab that just is the world's highest powered magnetic field laboratory. It studies everything from MRI all the way to quantum materials. And I'm really proud to be back in the state of Florida and really happy to be here and hoping to do business with many of you that I haven't met already. So thank you very much.
Hi, I am Michael Shatruk. I'm a director of Florida State University Quantum Initiative and a faculty in chemistry and biochemistry, and user of MagLab facilities as well.
Hi, good afternoon. Thank you, Matt. Thank you, Kelly, and your team for organizing this wonderful conference and for giving us the opportunity to join this conversation. My name is Feng. I'm a professor in electrical and computer engineering, and also with a joint appointment as a graduate professor in physics in University of Florida at Gainesville. Because of that, I can recruit students from both engineering and physics department to do research in my lab. In terms of research, we work on advanced semiconductor materials and devices and engineer them into transducers. Transducers mean we can convert signal from one domain to another, from mechanical to optical, from optical to electrical, and back to mechanical, and with some magnetic materials as well. And in terms of teaching, I teach introduction to quantum devices and quantum engineering, so I'm a hardware engineer. Thank you.
Wille, I'm the chair of the physics department and professor of physics at Florida Atlantic University. And at my university, in my department, we have three main efforts in quantum, broadly defined. We have a team working on loop quantum gravity. That's probably going to be the next quantum theory 10 or 15 years down the road when people can figure out how to make loop quantum gravity actually work. But the whole idea of combining general relativity with quantum mechanics is extremely appealing and also extremely challenging. Then we have a group working on quantum communication with drones, the entangled photons sent to drones and then back to ground stations. That's in collaboration with the Air Force Office of Research. And we also have a team working on in solid state physics, looking at skyrmions, Andrea phonons, you name it, all these exotic particles that one day may be used as qubits. Personal anecdote, in 1986, I was a very young postdoc at UC Berkeley, and down the hallway was the team by John Clark. So I feel like I came really close to a Nobel Prize. Thank you.
He's a wonderful man, John Clark.
Can you hear me? Okay, yes. First off, thank you for so many people staying this late for this event. And I'm Chen from the University of South Florida. My background is somewhat quite different from the other panelists because I'm not with the Department of Physics. And my entire career is basically working on the engineering, particularly about the system engineering. But however, I can share a little bit story about myself is when I was young and for the first 2 years of the college, my dream was to be a theoretical physicist in quantum mechanics. But when I turned age 20, I decided I'm not smart enough and let me go back to the engineering. I am also the entrepreneur. I started my own semiconductor companies back to some years ago, and after 4 years, the company was acquired by one of the largest company in the world. And so my background will be quite diverse, and is going to share maybe some kind of different view about the entire industry. Thank you.
Hello. Is it working? Well, thank you very much for being here until the very end. My name is Eduardo Mucciolo. I'm a professor of physics at the University of Central Florida. My background is theoretical condensed matter physics, but about 22 years ago, I started to drift more and more into quantum computing. So I've been working in this field since then, mostly quantum simulations, quantum algorithms, sometimes quantum error correction, and I've been a practitioner of quantum for quite a bit of time. Some of the founders that we saw today, at least in the companies that we saw today, I remember them when they were graduate students, actually. We were kind of contemporary. So it's a pleasure to be here, and I hope we will, we'll help you get a better understanding how the Florida universities actually are involved with quantum and how we can, steer and foster this initiative.
So I'm sure everyone in the room completely understands everything that everyone said that they do on stage now that they've been through their journey of quantum today. One of the privileges that I get is to talk to people like this on a regular daily basis, and it really is such an honor, and it's an area where I get to stretch my brain and imagination every day and seeing the incredible developments that they make. And in a former life, I was in a creative space, and today I kind of jokingly always say that I'm actually meeting more creative people in the life that I live now than I did when I was in the creative industry. And it's, again, people like you that are really thinking outside the box. Mike, I'm gonna throw it to you really quick. You guys have been doing this for a while. You and I had a conversation a few weeks ago about the communications and the fact that there's been a huge lack of awareness of all of the incredible work that you guys are doing. What are some areas that the folks in the room can pay attention to or start learning from to get involved?
Thank you. Well, it's, where do I start? So there are a lot of, I think there is a lot of information that universities put out in quantum realm, and there are a lot of initiatives that each of us represent here. We're trying to boost that space, information space, put more things online. But really, I think what's really important is to have some sort of unified effort where we collaborate more, interact, share, our experiences. We want to increase the education, and for example, at FSU we already have quantum information courses for graduate, undergraduate, even high school students. And I think popularizing this throughout the entire state university system, state colleges, will help a lot to spread the word. Now imagine like a high school kid, going to school, coming back home and telling people, telling parents, oh, I learned about superposition of about qubit. They're like, what the heck is this, right? But that could be a cool.
It's a
cool
Lego,
thing to
right?
do. Right. It's a Lego, right? And it's Lego, right? It's plural. It's still Lego. So as you learn, but I think we need to put this more of this information out. Really work closer within this. MOU should be really helpful for FAQT. Really connect people on multiple levels, and that will help a lot.
Who wants to take a stab at, sort of the significance of the MOU today that we saw being signed earlier?
I can go first. I think it's very important because kind of organically, the universities in Florida, most of them have been working in this area for a while, but without really a lot of coordination strategy. I think having this MOU is going to allow us to collaborate even more meaningfully and really move forward coherently in this field, so we can, share experiences. We're going to be forced to work together in several areas, right? Because now we're going to be sharing resources and stuff like this. So I think this is the main reason for being very optimistic and about this.
Does it still apply on Saturdays?
Yeah, we academics work every day of the week, unfortunately.
I think he's talking about football, but I could be wrong.
It was my crack at trying to make a sports joke, even though I'm the world's non-sports person. So that was it. But tell me a bit about you all independently have some of these centers, and you just heard President Parker announce the Palm Beach State College Quantum Center. In this collaborative nature, what can we start to see with centers that you all have, sort of bridging these gaps, and also I would say collaborating from a funding and also physical nature of what you guys will be able to do in those labs?
Did you want me to start?
Sure.
Sure, okay, so we have like a 30-year history of an incredible collaboration between three incredible institutions. And I think what's just so wonderful about it is you have collaboration across all of these different sites, and people get to know, hey, for example, Michael has this incredible thing he's doing, with Steve Hill at the Magnet Lab, and we can bring microwaves and cryogenics and high magnetic fields all together to make that happen, for example, because we have this incredible capability there. Or if some other group has incredible things going on in high-powered computing, like the University of Florida does, with its collaborations with NVIDIA, all of these things, we can help each other out to play to our strengths. And we can send, people that we want to collaborate to the right people. And we do that all the time at the Magnet Lab. Like we have a very high pulsed field facility that can do things but with very, 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 very fast timing. And then we have a DC field facility that can hold fields for a very long time. And those two facilities collaborate very strongly together and send users back and forth. So it becomes, everybody rises together, and you can do even more science and engineering together that way.
So Philip, she kind of touched on what you guys are doing with the NVIDIA lab. I'd be curious to get your perspective, and it was mentioned a little bit on stage earlier, but how does, NVIDIA's popular, it's in the news every day, people are seemingly understanding what GPUs can do. How does GPU and quantum or QPU kind of play into a mesh?
So UF has the privilege to start the University Plus NVIDIA initiative in 2020, I think. There was $75 million invested in installing the most powerful supercomputer among any academic campus. I think our Chief Information Officer, Elias, is sitting there. He can add more later if you want. And after 5 years, the system is currently being upgraded to generation 4. That's a lot of added investment. And in that new platform, I think now supports more than 300 research groups and 3,500 researchers running the system, doing all sorts of computation from quantum chemistry, AB initial calculations for biomolecules and semiconductors, all the way to design of macroscopic systems, and also supporting College of Medicine research. And that system, We also have a lot of seminars and visits from NVIDIA researchers who recently, for example, in April, come to the Florida Quantum Summit where we were hosting. They stayed extra days to give tutorials and seminars to talk about what you were mentioning, GPU plus CPU plus QPU platform. And some of our faculty researchers have already been adopting CUDA-Q platform in their teaching and their research. So we think this AI plus quantum initiative is actually very unique at UF, and also it's really exploiting or leveraging our existing capability. Currently, across the College of Engineering and College of Liberal Arts and Science, these are the two major colleges that involve quantum research and education. Our two deans from these two colleges are running this AI plus quantum initiative. Our Dean of College of Engineering is also in the audience. I think in this initiative, we're planning to hire strategically at least 4 or 5 faculty in the areas of quantum information, science, and technology in the coming 2 years.
So who on the panel can describe to the audience what it actually means in a branch between quantum and classical and using them together with AI? Who wants to take that?
Well, it's actually it's a very good question. So, in my view, at least, you can go both ways. You can use AI to improve quantum. We heard about that today, right? So, in the sense of optimizing new devices, new systems for quantum computing or quantum sensing, quantum communications. But you can go also the other way, which is what we heard today as well. So you can have quantum helping AI. I'm still kind of skeptical myself because I know the technical challenges of that. I think they are severe, right, to wholesale using quantum to do AI. But there are aspects of it that you actually can, quantum computing, for instance, that you can use to benefit AI. So it goes both ways. So I think the classical, which AI is a classical, essentially a classical algorithm or technique, can work very close with quantum, but we're just starting that. I think there's a lot more to understand in that front.
So when you guys are all working with students, what is the biggest area where you can excite them into learning more? And as we heard on the panel today, there is somewhat of a lack, or not enough students, especially that are American citizens graduating from some of these universities. But what can we do to really kind of gain more attraction into the space?
I think probably the biggest barrier right now is to raise the awareness about quantum technology and tell students what it really means to have a quantum computer and quantum sensing. What is the difference between a quantum system and a classical system? Therefore, it's really important to actually have a curriculum to tell students, not just students in physics, but students in engineering, students in biology, students in chemistry, maybe even students in medical school to be aware of this technology. I think that's really important to actually raise the awareness in that way.
And just one other thing, because I think, at all levels, starting at the youngest to the oldest, it's capturing that piece of curiosity, but also the fact that, hey, everybody can contribute and everybody really can learn. And if you're hands-on and you want to get hands-on, you can be a technician in this field. There are incredible opportunities for that, all the way up to PhDs. And it's capturing that curiosity and showing them that it's interesting and that they can be engaged, and that it's going to get them a good paying job being in the technology space. And I think quantum is one of the areas that's completely exploding right now. And it's really good to say, hey, this is an early up and coming area let's go do it. I mean, I've worked for years to keep people in superconductivity when it was tough, but now it's, luckily we have between fusion and what's going on in quantum, it's an exciting place to be. But in those tough times, it's like you can still get a good paying job, you know, being a technology person. I think that's really important.
And Matt, if I may compliment, so what I've been seeing, at least at UCF, is that the students are thirsty for quantum. They really want to get involved, and to a point that they were almost revolting because there were not enough courses, not enough opportunities, particularly for undergrads, to be involved with that. So at UCF, we created a very kind of foundational course that is accessible to anybody who has taken Physics 1, Physics 2, Calc 1, Calc 2, so the very basic courses that most engineers and scientists take. That's enough for them to actually get involved with quantum. So there's a course that is targeting that. And we saw an exponential growth in interest in this course. So we started with some, just a physics majors taking the course, and now it's pretty much, all engineering, computer science are really interested in taking that. So I think we have to provide more opportunities like this to our students. And I think it's almost like it's going to happen because it's already there in their minds that this is where they want to go.
Yeah, maybe I can share a little bit because right now, almost all my PhD students in the quantum computing and communication areas are the US citizen. They grew up in the States, and many actually in Florida. And most people expect I'm going to get lots of international students, but it's actually not the story. And also I can share because a few weeks ago, I think the DoD officer actually applied to see my labs, and they're curious about what we have been achieved. And I just told them, just look at the American kid can do the quantum engineering very well. And it's not only just science, because I already explained my background here may be different from the others. Everyone's from the physics. I'm from the engineering. And when we keep talking about the quantum information sciences, I always mention quantum information engineering will be more important. I always repeat this story. So which nation is actually leading the world in semiconductor sciences? United States. Which country is leading semiconductor engineering?
Taiwan.
Yes. So this is actually a good example. I spent a good portion of my time for career in Taiwan, so I guess I know both places pretty well. So I guess one of the biggest threats for not only for the state but also for the nation is we just consider consider about the quantum sciences, and no matter how many Nobel Prize the winner we're going to get, it's not going to be a successful industry. And finally, we have to compete with the other nations, and across the Pacific, they have tons of the engineers. Mm-hmm. And so we need to let our kids understand. So I always explain to my students what is our project working on. I feel I was lucky to support by the US military to work on the subject, say, okay, we need to compete with one competitor who has like 100 times or even 1,000 times more resources than us. But as long as we are smart, we are going to do something amazing. And so there will be always some kids feel very excited, and then we can show that we can do it. So that is some important message I guess we need to let our kids know. They will be able to be successful in STEM. It's not only because the international student can do it, American kids can do the same job.
Yeah, if I just may, I want to jump back a little bit on what Eduardo said. I think students are excited. I think opportunities need to come along. When I got involved in the quantum science, which was not that long ago, I was really kind of dilettante in that. I had no idea what was going on. I actually took the course. I registered for the course at FSU, which Nick Bonsteel, my colleague, taught. And I took the course. I'm a chemist, by the way. I'm not a physicist. And it changed totally my mind about the field. I thought like before that, I was like, I don't think this is promising. This is just a bubble. After Nick's course, I know this will work. The quantum technologies will happen. They're already happening, we saw. And I think what we're really trying to do is get students early on. Like we have this signature discovery days at FSU every year in October. They're going to happen 2 weeks from now. So our VP, Stacy Patterson, who signed the MOU, she organizes these. And this year we have 3-hour long event called What is Quantum? just directed at undergraduate students, so they can come, and faculty from MagLab, physics, chemistry will be giving brief talks, telling them what it is all about. You know, what's superposition, what's this, what's that, and that will result in them coming to the labs, you know, learning more about quantum. We actually will have the quantum certificate program in place from fall for graduate and undergraduate students. And I think we have to distribute this more broadly. Again, we're happy to share all our experiences with every school in the state. And I think it will build this ecosystem that people talk about very quickly. I think MOU will be a big deal, you know, here, big help.
So can I add another element in attracting students' interests and training students is to get students to be involved in research early on, even for undergraduate students in their first year and second year. And you have them to actually work in the lab in a hands-on fashion on real research projects that will let them know what's actually going on at the frontier of research, and also they will understand what it actually takes to, for example, set up an experiment. In order to set up a quantum mechanics system, a quantum system, you actually need a lot of classical controllers to control them. You need optics, you need mechanics, you need cryogenics, and those will be related with the job opportunities in the future, because those will be the industries and the technologies that will enable quantum technology in the real life. And I think that's one way the students that needs to actually realize that's the case.
And it's starting with the flywheel too, because there needs to be businesses that are demanding talent. And I think that we're certainly entering into that era now, especially because the technology has evolved so much over the last couple of years. And you know, even what we were seeing on today on what people are you know, having claims around in the next couple of years and what they'll end up having in their technology stack, it's staggering when you start to think of it. We're not following Moore's law anymore. And the other thing that I want to really kind of highlight is we took you guys through a journey today talking about a lot of hardware. But the biggest thing that we also have to talk about are the applications, the sensors, the networking, and all of these other areas that really make up the quantum ecosystem. And they are all very unique on themselves. For the room, you know, we've got another, you know, sort of 30 minutes or so here. What are the takeaways that you all want this audience to have leaving here today, knowing that this is their introductory to quantum? Who wants to take that?
So that brings up a really good point, because we've been talking about quantum all day as if we know what we're talking about. And the first thing is, none of us know what quantum really is. It's a big mystery. And one of the, sort of looping back to recruiting students, so at FAU we have a class called First Year Seminar, in which we try to connect the students, the physics majors, to our department, because very often that connection doesn't happen until the junior year. And one of the things I do is I ask the students, well, why did you decide to become a physics major? What do you want to do when you grow up? Very few say they want to moderate panels. I don't know why that is, but and very few say I want to be a physics professor either. But there's basically two things. Half of the class wants either to go to Mars, and some of them might be happy to send there. The other half, they want to do quantum, and let's talk about it. So what do students at age 18 or so know? Well, they go like that. There's this cat, and it's alive and dead at the same time. That's pretty cool, kind of, unless you're a cat. And then, you know, if you run fast enough to a wall, you'll actually make it through that wall. Okay. Tunneling, that's crazy stuff as well. There's all these cool terms. There's a, you know, you give your girlfriend or your boyfriend a hug, and now you travel to the other side of the country, and you're still connected. You're entangled, theoretically. So quantum is crazy, and Richard Feynman, famous physicist, you have to quote Richard Feynman in a lecture, said anybody who claims to understand quantum is showing that they haven't understood it in the first place. So it's still a big mystery, which leads one to believe that maybe there's still some aspects of quantum that we need to discover, and maybe there are still some applications that we need to discover. It's sort of usually the big three, right? It's quantum computing, quantum sensing, and then quantum communication / cryptography. Maybe there are areas there that we haven't even thought about yet, and that's really exciting. That's why we're in this business.
So I love that, and I especially love the understanding quantum quote from Feynman, because I never understood it. I could just do the math, and the math showed me that it worked. But it just to me, it's phenomenal to be part of an area that discovers, and being part of a lab that's discovered these materials, for the 30 years it's been in business. We started on graphene right at the beginning, and now Google's looking at that for quantum computing. We do topological materials that are still under huge amounts of research now that Microsoft is looking at for chips. Oh, sorry.
Dimitri about that.
Oh, definitely. I'd love to talk to Dimitri about that. That would be great. But I think that what I think is really important to understand is that Florida has been in this business for the last 30 years, and probably even before that, because there are people that were doing it before that at the big universities here. And this group of people, and many others in the audience and not even in this room, are doing phenomenal work in that space. We have millikelvin facilities that go to the lowest noise levels in the world at the University of Florida. We have millikelvin facilities at FSU too that aren't quite as low noise as theirs are, but they're still pretty good, and we all work together as one big team to make that happen. I think that there's incredible capabilities in the Florida that businesses can use today, even for startups that don't have the resources that big companies do. And I think this MOU, hopefully is going to open those capabilities up to everybody, and we're going to work as a team to get those out to everybody to know where the skill sets are for the people that can help you be successful. I've worked in industry. I've worked at a big DOE national lab. Now I'm working at the only national lab in the state of Florida that's an NSF lab. So we're fundamental. Like, we've looked at fundamental stuff. We want to be able to help people, take that forward into products too. So you guys pay a lot of tax dollars, both to the state and the federal government. So make sure you're utilizing what those resources are paying for, because we're resources for you guys. So that's one thing I just want to say. And if you're ever up in Tallahassee, we're happy to give you a tour and introduce you to everybody, no matter what your line of business is. So thank you very much.
And Matt, just to add towards your question, so if people want to have a take-home message, I think quantum now cuts across many disciplines. It started in physics, but actually physicists are no longer the biggest players in the field. I think it definitely moved more towards engineering, computer science, materials. It's actually very broad right now. So it's not just a physicist's game. It hasn't been now for a few years. Some physicists haven't realized that yet. So what I think people have to understand is that it's going to be pervasive, because it's going to be everywhere. It's going to cut through, it's going to involve, maybe people from business, maybe from areas, health sciences. It's going to be pretty, widespread. And we can see that already happening in academia, right? So when I got here, I was the only one talking about quantum computing. I was a physicist, nobody else at UCF. And now eventually I start to see a little people here and there. Now we have multiple colleges actually working on this field, right? So multiple disciplines, people who were not interested maybe 10, 20 years ago. Now they're fully vested into it. So I think that's another message, make sure that you understand this is going to be everywhere.
I also want to add that I think quantum is quite unique, because, okay, let's take a look at AI. AI has been around for a while, from academic viewpoint, and it's very well established technology. And we have companies basically owning it now, right? NVIDIA, Google, But I think quantum is the area where you still need fundamental research coupled to invention, innovation, and commercialization. So the companies cannot do this. Basically, that's what CEOs of Google, Microsoft, IBM told the Congress. They said, we cannot do this without fundamental research a few years ago. And I just want, if there are company, industry representatives here or general public, universities are the resource to develop the workforce in this state, in all states, in the entire nation. But if we want to do this in Florida, we have to couple better private sector with academia, industry with research. And again, MOU I think is great. We need to continue these efforts. We need to keep this Quantum Beach event, I think, every year. And I said, in spring, we're planning to do every year, every spring we'll have Florida Quantum Conference that will be more academic leaning and traveling around the state. We've been running this kind of at FSU for the last 4 years, but we really want to start moving it around, and Philip and Eduardo are very interested in hosting this. So please, keep your eyes open, engage with us more. If you're from the company, email any of these gentlemen, lady, myself, we'll be glad to engage with industries and work with you guys, because I think we have something to offer, and I think you have something to gain from this interaction.
So somebody said on a panel a few weeks ago, if we spend billions on investment today for quantum, but we could spend trillions on defense later on. That's a huge, staggering statistic when you start to really quantify it, right? What are some of the things that we need to really be focusing on right now on the advancements? And also, I kind of think that everyone that I've spoken to that are sort of outsiders or still learning about it a little bit, the common misconception is, oh, this seems too early, or it's still 5 years away. Who wants to take a stab at that? Philip, you look like you really want to go at that one.
Can you repeat the second half of the question?
So the second half is, are we 5 years away from quantum, from more advancements happening?
Earlier I want to address the take-home message. Actually, this is probably we can start with this very impressive, audacious roadmap from IonQ. They say in 5 years, earlier mentioned today, 5 to 6 years, it will scale up to 2 million physical qubits, and roughly maybe 1 million, or slightly less than 1 million. No, probably 100,000 logic qubits with the error rate of 10 to the minus 5. I think that's very exciting and inspiring. We as educators like to study that type of advancement and translate to our student, to the class, right? And then quickly, this will benefit the workforce. In the meantime, I think that's also too slow. We would like to invite industry researchers and recruiters come to our department, our College of Engineering and Science and Arts and Science to give seminars and also career fair presentations to generate this strong polling force to our students. We have the privilege to have some of the smartest students in the state and in the nation, also many really excellent students from all over the world. And at university classroom, we are doing very well in telling the compelling intellectual stories like the Nobel Prize winning work, basic science, to do curiosity coupled. A student offer the curiosity, we offer this encouraging, inspiring scientific discovery stories. That's a bottom-up driving force in education and teaching. But we really we can benefit from that's industry polling. We need more internship offered by companies to our students to open the door so that they can get hands-on experience. And then when they come back to finish their PhD or undergraduate senior design project, they have much more input to steer that can shorten their training time when they go to the company. We also need entrepreneurs like you and others come to campus and give very encouraging presentation, short courses to our students. I think that will be very helpful as well. In terms of the advancement in next 5 years, I think you earlier mentioned there is a very diverse hardware platform. We heard this a very impressive roadmap from IonQ, but also from D-Wave. They have this both gate-based and also annealer-based quantum advantage development, they're also talking about thousands of qubits. I think all this, plus the superconducting platform and other integrated photonics compatible platforms in the next 5 years, there will be a lot of solid development. Some of our best students ask tough questions, mostly toward the tangible benefits and advantages that quantum can offer, because that will be also very strong motivation for the workforce development. If students should choose to learn quantum computer or they choose to study GPUs, it really depends which one can deliver tangible benefit if they build a circuit that they can really feel strong satisfaction for their own work.
So I'm gonna.
That's my observation. Thank you.
I'm gonna start at the end and work our way back. But what, sort of, where do you see us going in the next 5 years?
UCF, you mean? Yeah.
Sure.
Okay. So, well, at UCF, I think we've been very fortunate to have received a lot of funding from the state that has allowed us to hire excellent quantum faculty in the last few years. So we went from a few to more than 20 people actually right now working in this area. So we feel like the future is bright because we have very good infrastructure. Obviously we can always improve. We have the people. We may have we need a little bit of investment here, there to complement and supplement some things that we're lacking a little bit here, there, but it's not too hard. But I feel like, once we have all these pieces in place, and especially now with the state actually, willing to pour more resources and working out with the other universities, I think we're going to be able to scale up tremendously the amount of research we do in this area, the amount of students that we actually educate in this area, and also the opportunities that we can provide to them. So I think it's going to be extremely exciting for the next 5-10 years in this area, especially at the State University in Florida, given all the momentum that we are starting to see.
I would like to offer a little bit similar but slightly different view. I have been, although I'm a professor, I have been in industry closely, and I also, in my career, I value probably like a 200 business proposal in my life. And I would like to share a little bit is, if you were a senior executive of a big companies in 2002, just after the internet bubble, what do you think? If you were the senior executive in the late 1980s, just after the first bubble of AI, and what you are going to think. This is going to be some practical stuff about the quantum. The quantum industries is going to be the $1 trillion, that's for sure. And it's not going to be very far away, but it's not a straight line. And similarly, the industry situation going to impact the motivation for students getting into these areas. At this moment, I think it'll be great because the entire nation just shortage of engineers and shortage of the scientists, including the physics and the mathematicians in the areas. And but however, most people probably do not realize why I got several students working with me for the PhDs. I just explained to them, in quantum industries, if you want to have the bachelor degree, it's not going to be useful. If you're ask them, you just go to the, look into the job opening for all the big companies. It's all require PhD. There's lots of the reason behind is that if we provide any kind of course to educate the students, one of my biggest headache is students today don't know much about the physics in engineering, and how can we teach? And luckily, I'm familiar with a former department chair of I just don't mention the name, one of the top university in the double in computer science. And he also chatted with me, how do you guys educate the students? Because then I realized even in their top universities, which is even much higher ranking than the Gators, they still have the problem. So this is actually, I guess, again, that's for all this kind of Florida Alliance, I think there will be a good brainstorming and how can we create not only a comparing program, but it's actually effective program. And can we expect a computer science student to know about quantum mechanics? The answer is no. There are so many things they need to learn in such a short time.
I disagree.
There are so many things they need to know. So at least my approach is, how can I let the student spending minimum amount of time in quantum mechanics, but they will be able to go in depth. I cannot say no. They have to learn something, but this is the problem. If anyone managed the entire department of the college or even the university curriculum, and they're going to know, everyone tries to say this is important, that is important. This limit amount of time. But let's go back to engineering. It's not going to be industry. It's not going to be the straight lines. What happened, but it does not change the final situation. People already learn enough experience from the AI, from the semiconductors. And the entire development speed in the quantum will be much faster than semiconductor industry, much faster than the AI industry, and much faster than internet industries. And I always tell my students, if there is any bubble for quantum, that is a great opportunity.
We're gonna move through quick. We have 10 minutes left, so we'll get down the list.
Matt, you're asking me to predict the future, and as you know, that's really hard, predicting especially the future. But I do want to make a point, though. I'm a college professor, so I'm going to go off on a slight tangent, because we've all been deluding ourselves here, making a distinction between classical computers and quantum computers. But guess what the classical computers are based on? They're based on semiconductors. And guess what semiconductors are based on? They're based on quantum mechanics, band gaps, doping, you name it. So quantum was always there. And I think the point is, if you had in the early 50s, when semiconductors were really being developed, had asked what the applications would have been, people would have been completely wrong. So the future looks very promising. The details, we're going to be surprised. We're going to sit here hopefully 5 years from now and go like, wow, we totally didn't see this coming. So prepare for surprises, but be ready that they're coming.
Really? Really? 5 years, the plans, we have lots of plans. We started only 3 years ago with support from FSU president and VP for research, and they've been super supportive of what we're doing. So we've been really, I think, lucky to have such a huge support from our administration. We started, with just 19 faculty who identify with quantum. We hired 9 new faculty over the last 2 years, and we're searching for 2 more right now, and I'm sure it's not going to stop there. So now we have 44. But what I'm most excited about is not with the number, but that we started with basically like 2 departments, and now we have 7 involved. We integrate with MagLab a lot because we're next door to each other. It's just really exciting because people come to us now and they say, how can we participate? Like before, we're like, oh, quantum is weird. We don't know what it is. Now we actually see people engaging with Quantum Initiative, trying to take part in this. We have faculty, solving transportation problems, and they're trying to think how to use quantum computing. People alluded to that earlier today in the earlier panel. So I think one thing we want to see is like this inclusive environment where we keep growing. We want to see very strong workforce development. I'm sure we'll have quantum degrees, master's, PhD for sure, probably also like on a bachelor level, some kind of majors in 5 years. And we also set up this strategic, what I call quantum moonshots. Those are areas that our quantum initiative really wants to target, like quantum networks, new qubit modalities, some things that industries don't do yet. We want to be innovative. We want to open new opportunities, like you were saying. Things are unpredictable. We don't know what's going to happen, but if we do our work well and we innovate, we'll open new possibilities for an entire, STEM area, and I think that's what's really exciting.
No, I absolutely agree with the last two speakers. I mean, I think that what is so exciting is the incredible multidisciplinary aspect of quantum, just like working on big magnets, which is where I've spent much of my career. And that's what drew me into that. And I just think it's phenomenal, you know, the quantum initiative that all of these universities are establishing. And Michael, your inclusiveness at FSU has been phenomenal across all of these different departments. And I love engineers, by the way. I know I'm a physicist by training, but I do have an appointment in the College of Engineering because I've worked with engineers enough. So I really believe in the power of bringing all of these disciplines together. Innovation happens at the boundaries. And that's what's so exciting about quantum. We can't see where it's going, but again, you know, I think over the next 5 years, this incredible team of people that you see here on the stage is going to come together to make it happen, utilizing resources that we already have available, along with new ones that are going to come along in areas that we can't even predict. So, I think you know, the future is very bright in quantum, and it's absolutely critical. I think you mentioned, you know, we could spend trillions of dollars on defense later, assuming we survive the first wave of quantum attacks. So I think we need to, you know, from a national security perspective, invest in this too and put all these great minds to work on it. But I think it's going to do a lot of great things in medicine, which I'm super excited about. I watched what AI did in MRI. I can't even imagine what quantum's going to do in healthcare. It's going to be incredible. So thank you.
So at the University of Miami, we are really proud and excited to be part of this State Quantum Alliance. And the leadership at UM has recognized the importance of quantum research early on, and they started a quantum initiative about 3 years ago, through which allowed a lot of new hiring. And then the number of faculty members working in this area has increased by 80%. So we now have 16 faculty working in the area of quantum research. And this group of people, along with students and postdocs and other researchers in their group, we have at least 2 goals. The first goal is to really push the boundary of the fundamental research and try to tackle some of the most difficult problems in the fundamental research. The second goal is to train the workforce, is the education. So there are 2 different channels. The traditional pathway is to train graduate students, PhDs, in the research lab. But we also are going to have programs that are going to be facing a more general population of students, not just PhD students, right? And then in terms of the application, one advantage at the University of Miami is that we have a really big medical school. So our quantum initiative have collaborations with researchers from the medical school, focusing on potential applications in the medical applications such as quantum sensing, quantum imaging, and also applications of quantum computing in solving problems in medical research. And that will be our plan.
So I would like to open up, if one person has a question, we're limited on time, but does anyone have any questions? No? Well, with that said, I really cannot thank you all for participating today and being here. It is incredible what your work is doing and the bright minds that you're educating, and really applaud you guys so much. Thank you for being here. And thank you all for listening today and being part of this conversation. Hopefully we've given a little bit of information around what is quantum, and you walk away telling a couple other people that you know something a little bit more interesting today. And again, I want to thank our sponsors. I want to thank the BDB for really putting this together and the entire team there. I want to thank all the people behind the scenes today, the people that are bringing us water and amazing meals, and all the tech people here that have really made this all possible. So thank you all for coming today, and we'll see you outside.
Well,